Chapter 4, Section 5, Integration by Substitution. Alright, now when we integrate composite functions, we want to be able to hopefully be able to recognize a pattern for our integration. And it's what we sometimes call U substitution. We let U represent like the inside function of a composite function, the inner, to set up something that's easier for us to integrate. Now it's a little more complicated than that, but do you remember with the chain rule for differentiation, when we took the derivative of capital F of g of x, we got the derivative f prime of the outer function with respect to the inner function times the derivative of the inner function. So we have to kind of reverse that. We're going to make this part here our inner function. We're going to call that u, and then this part here will be our du, which hopefully will be some kind of g prime of x dx expression. So we have to make sure everything's set up perfect. As I mentioned, and I will mention again, you can take the derivative of just about anything, but when you integrate, you have to have it set up perfectly. So here's the theorem that allows us to use anti-differentiation or to integrate a composite function. Let g be a function whose range is in the interval I, and let f be a function that's continuous on I. If g is differentiable in its domain and f has an capital F is an antiderivative lowercase letter on I, then the integral, notice here, composite function of f of g of x times g prime of x dx is equal to, notice the antiderivative capital F of g of x of the inside function plus a constant, because this is an indefinite integral. I'll show you how to do definite integrals in composite functions pretty soon. So if we use the substitution, if we do what we call the u substitution, if we let u equal g of x, then du, in terms of differentials, would be the derivative of this, g prime of x dx. And then if we actually make the substitution and plug right into here what u is equal to, and then of course this would be du, we would get the integral of lowercase letter f of u du is equal to capital F of u plus c. Okay, be careful here. All right, careful, don't add another constant. So I'm going to show you how to do this by actually recognizing a pattern. Okay, now you can use a substitution here, and I'm going to show you that as well, but for right now I'm going to just identify the pattern. So what I'm going to do, I'm not going to integrate these, I'm just going to find the pattern. This is the main part of my integrand, because this is the composite function. This is just the good old 3x squared here. I'm going to let the inside function right here be my u. That's x to the third plus 1. Okay? So what's the derivative of x to the third plus 1? Don't look over here anymore. What's with du then would be the derivative of this, which is 3x squared dx. Notice that that is also present. The 3x squared and the dx is all there. This guy is set to integrate. I can integrate this using, and I'm going to show you examples like this using a substitution. I'm just not going to do it yet. This guy here, as you can see, this is the main part of my integrand because it's my composite function. This is the same as x squared plus 5 to the 1/2 power. So what I'm going to do is I'm going to let this part right here, x squared plus 5, the inside, be my u. So that means that my du would be the derivative of this, 2x dx. You can see now again why way back at the end of chapter 3 we were taking derivatives in terms of differentials. And it's all there. There's my u right here, raised to the 1/2 power, or the square root of it, and this part right here is present, and that's my du. If I don't have this here, I can't integrate. Now in this problem, this looks more like this part would be the main part of the integrand, because it's a composite function. It's your inside function is the secant of x, and the outside function is the square. Well, that's not going to work. What we have to do here is we have to make this part of the expression, think of it to the 1st power. This is the main part of the integrand. This is my composite function. Now I've been wondering, well, why would I do that? Well, if my inside function is the secant of x, then the derivative of secant of x is secant of x tangent of x, and I don't have that. However, if this is my u, the tangent of x plus 10, and it's going to take some practice to get good at this, then my du would be the derivative of the tangent of x plus 10, which is secant squared x dx, and that is all here. So it has to be set up. You may have to play around with these when you're first working them out to see you can get the right pattern here and recognize the pattern so that you can set up your integration. All right, speaking of setting up my integration, oh, wait, I have one more like this. I'm sorry, one more. Here we go. All right, here we go, one more, and then we'll do some integration here. I have this part being the main part of my function. It's a little more obvious here. And so that means that this would be my inside function. So my u would be x to the third plus 1. So my du would be 3x squared dx. Uh-oh, there's a problem. 3x squared dx, that's not what I have here. I have 6x squared dx. Well, the problem is that this is supposed to be a 3 and I have a 6 here. Now we know that 6 is 3 times 2. So we could think of 6 as 3 times 2 and just bring the 2 out in front as a scalar multiple here. We can bring the 2 out in front and think of this as 2 times 3x squared. And now it's all set up. The du is present. The du has to be present to do the integration here. That's what this is saying here. The du has to be present to be able to do this integration. All right, now let's do some integration. Very much like this last example, this right here is the main part of my integrand. So this is a composite function. This would be the inside function, the x squared plus 5. The outside function would be raising it to the power of 5. I'm going to let u equal x squared plus 5, which means that du would be 2x dx, which happens to be there. So now if I actually substitute and plug in, use my u substitution, I would get the integral. And for that would be u. This would be u to the fifth. And then in for the part that's underlined in red, that's my du. Well, I know how to integrate that. We learned that back in section 1 of this chapter. This is going to go up to 6 over 6. I am going to get 1/6 u to the 6th plus a constant. And I would be all done except for one thing. I started with integrating an expression that was in terms of x, and I have this in terms of u. I don't want to finish the problem and leave it in terms of u. I want to put it back in terms of x, so that's where the substitution. That's why I write it out over here. Now I'm going to plug this in for u right there. So I end up with, here, I'll put it right below, 1/6 the expression x squared plus 5 raised to the 6th power and my constant. And that is what this integrates into. Let's try another one here. This is the main part of my integrand. Cosine of 15x, this would be my inside function. Cosine would be my outside function. So I'm going to let u be 15x, which means that du would be 15 dx. Well, there's my cosine 15x. Look right here. There's my du. That's a u there. It's hard to see because I write so poorly. So now I'm going to be able to integrate this using anti-differentiation of a composite function, that theorem that we just stated a little bit ago, by first substituting in using my u substitution. So in for 15x, I'm going to put a u here. So that's going to give me the integral of the cosine of u. And then the part that's underlined in red, the 15 dx, that's my du. And look how simple this is. I no longer have that composite function to deal with. I have a simple function, but it's in terms of a different variable. It's in terms of u. This is going to be the sine of u plus a constant. And again, we didn't start with u as our variable. We started with x, so let's not finish with it. Let's finish with x. So make a substitution back in, and I get the sine of, I'll put in parentheses, 15x plus my constant. Make sure that you plug back in. All right, so far so good. First two examples, not so bad. Let's try another one. All right, so this is the main part of my integrand. This is my composite function. My inside function would be x to the 4th minus 3. My outside function would be the exponent 4 there. So what I'm going to do is I'm going to let u be the inside function, x to the 4th minus 3. So my du would be 4x to the 3rd dx. And we have a problem. I need the 4 in there. All I have is x to the 3rd dx. I just have this part right here. I need the 4 in there. Well, as long as it's a factor of a constant that we need, as part of our integrand here, I can handle that, because with a constant, I can think, and although I doubt if I would write it out this way, but I can think of getting that 4 in there by thinking of this as 1/4 times 4 x to the third times the quantity x to the fourth minus 3 to the fourth dx. See, all I did was I put this inside my integrand, because 1/4 times 4 is just 1, and I'm not changing anything when you multiply by a factor of 1. But now this allows me to bring the 1/4 factor using the scalar multiple rule there. I can bring that 1/4 out in front, and now I have 1/4 the integral of 4x to the third times the quantity x to the fourth minus 3 to the fourth power dx. And as you can see, I have everything I need right here. So now I'll make my substitution. I'll leave the 1/4 out in front. It's a constant. It's not affecting the substitution. This part here is my u. So I have u to the fourth. And then the underlying part there in red is my du. Well, look how nice this is. Up to 5 over 5. Now I have a 1/4 out in front, so over 5 that would be 1/20 u to the fifth plus c. And then, as you probably, or at least hopefully, are assuming we're not done, we have to put it back in terms of the original variable, so we make the substitution back in, and I have 1/20 the expression of the quantity x to the fourth minus 3 is my u to the fifth power plus my constant. All right, now that's called pattern recognition, and we use a u substitution. Now we're going to use a u substitution in these next examples, but so far so good here. That's what we're going to do. Okay, that's how we're going to set them up. We're going to find our u, we're going to find our du, and we'll hopefully that our du will already be in the integrand. If not, and we have to finagle the constant, which is what I like to call it, then we'll set that up. Now in this problem, I do have a composite function here. This is 3x minus 2 to the 1/2 power dx. So this is my inside function. My u is 3x dx. So my du would be 3 dx. So I'm going to change my variables, but I have to finagle the constant because I have the dx. I just don't have the 3. So remember what I did with the 4 back here? I put a 1/4 times 4. Well, this would be like a 1/3 times 3. I'm going to write it like this. 1/3 on the outside, the integral of 3 times the quantity 3x minus 2 to the 1/2 dx on the inside. Okay? Now, the book wants you to recognize patterns from the very beginning. And I understand recognizing the patterns here, but I like to make the u substitutions when we're doing this. Now, in the textbook, they talk about these problems being the actual substitution. No, you can substitute in back here as well as what we're going to do here with these examples. So I don't want you to get thrown off by that, because I started looking at what I had written down there, and that might be a little confusing. Like, well, were we supposed to substitute back then? Yes, we can. I wrote this down in terms of what the textbook was saying. So now, this is going to be 1/3 the integral. This is going to be u to the 1/2, and all of this part right here is going to be my du. So up to 3/2 over 3/2, which is the same as dividing by 3/2, same as multiplying by 2/3. So I get 2/9 u to the 3/2 plus c. Let's plug back in for u. It's 3. I wrote 3x dx. Good Lord, where's my mind? 3x minus 2. That's what gave me the derivative of 3. Sometimes I don't think I can walk and chew gum at the same time anymore. 3x minus 2 to the 3/2 power plus my constant. There's my answer. Now this one has got a nice little twist to it, because I have an extra factor of x here that's not part of my du. So this is going to be a little bit more interesting, but still start out the same way. That's the main part of my function. It's a composite. The main part of my integrand is a composite. So the inside function would be the 2x plus 1. So I'm going to let u equal 2x plus 1. Du would be 2 dx. So I don't have a 2. That'd be easy. But I have an x. And that's not so easy. You can't pop the x out in front, only a constant. So this is going to be a problem. That x being in there is going to kind of gum up the works a little bit, and I'm not going to be able to integrate. So I take this guy here, and I solve for x. U equals 2x plus 1, subtract 1. I get 2x equals u minus 1. Divide by 2, I get x equals 1/2 u minus 1/2. I can plug in and get this all in terms of u if I'm careful here. Now, first things first, I have to finagle my constant. I need the 2 dx. I have the dx. I need the 2. So I'll put the 2 here and the 1/2 here. So right now, look what I have here. I have 1/2 the integral. So this part x is right here. This is the expression 1/2 u minus 1/2. This part right here, this is my u, the square root of it, so that's u to the 1/2. And then the 2 and the dx, the 2 and the dx is my du. Now what I'm going to do is I'm going to factor out the half because I don't like those fractions in there. My du, I got to write it down. And I'm going to pop that half out in front where there's already a half, so that's going to give me a 1/4. The integral of, and I'm going to write this as u minus 1, u to the 1/2 du. I'm going to distribute through. I'm going to have 1/4 the integral of u to the 3/2 minus u to the 1/2 du. And that took a little bit of working with this to get it to this form. So now I'm at a point where I can finally integrate this. So this is going to be, okay, 1/4 out in front. So I'm going to integrate this. I'm going to write this as 1/4. I'm just going to go ahead and do this. This is going to be up to 5/2. Over 5/2 is 2/5. So I have 2/5 u to the 5/2 minus up to 3/2 over 3/2. So that's minus 2/3 u to the 3/2 plus c. I did not give myself enough room here. So I'm going to distribute by the 1/4. I get 1/4 times 2/5 is what? 1/10. I get 1/10 u to the 5/2 minus 1/4 times 2/3. That'd be 1/6 u to the 3/2 plus c. Now I can plug back in. I'm going to plug in for u 2x plus 1. So this is 1/10 times the quantity 2x plus 1 to the 5/2 minus 1/6, that's a 6 there, not a u. 2x, the quantity 2x plus 1 to the 3/2 plus c, and there's my answer. And you don't have to factor out a quantity 2x plus 1 to the 3/2 out of the first couple of terms. You can just leave it like that. Whew, that one had some stuff to it. All right, so now one more example here, and then we'll give you some guidelines. The integral of the cosine cubed of 2x times the sine of 2x times dx. This is the main part of my integrand. So I'm going to let u be the inside function, which would be the cosine of 2x. So the u would be the cosine of 2x. My du, I'd have to do a chain rule here. It would be negative sine of 2x times 2 dx. That'd be negative 2 sine of 2x dx. Now, I got some work to do. I have most of this. I have this part. I need the negative 2. So it's time to finagle the constant. Where's my red pencil? I do my best finagling in red here. Okay. So I need a negative 2 here. I'm going to put a negative 2. I'm going to write this as negative 1/2. And then I'm going to put the negative 2 in here. Let me go back and write this. So this would be cosine cubed of 2x sine of 2x dx. Now I'm ready to do some substitution because now I have all of it. I have the entire negative 2 sine 2x dx for my du. Sounds like double talk. This is negative 1/2 the integral of u to the 3rd du. This is my u. Plug in, and then this is my du. This is easy. Up to 4 over 4. It's negative 1/8 u to the 4th plus a constant. I didn't start with u. I don't want to finish with u. This is negative 1/8. In for u is cosine to the 4th 2x plus a constant. And there's my guy. This is a little bit more involved. You're going to need to practice the snot out of this one here. Let's try giving some guidelines here. All right. Guidelines for making a change of variables. Pick your substitution. Inside function is typically your best bet. Make sure you know what du is. You have to rewrite it and put it in terms of u. And it doesn't say it, but you want to finagle the constant here if you need to. Then you find the resulting integral, have it in terms of u, plug back in, and get it in terms of x. And then, of course, you can check your answer by taking the derivative of it. Now, most of the problems that we have done that involve this have been something raised to a power. The something inside that's being raised to the power is my inside function, and that's what we call the general power rule. The general power rule says that if g is a differentiable function of x, and I am integrating g of x raised to the nth power g prime of x dx, that we just do the general power rule. We add 1 and divide by that. That's just the power rule for integration. We're just generalizing it as we have our u and our du here, right? And plus c. So we can put that in and notice that I get u to the n plus 1 over n plus 1 plus c, as long as my n does not equal a negative 1. So I can integrate these. This is not that bad. So that's what I have here in these next few examples. Okay, this first guy. This is my u, 2x plus 3. My du would be 2 dx. I don't have a 2 dx, I have a 5 dx. So I finagle the constant. I'm going to bring the 5 out in front, but I still need the 2 there. So I got a 5 out in front. I'm going to put the 2 there, so I'm going to put a half out in front. So that's 5 halves the integral of the quantity 2x plus 3 to the 3rd power dx. Now, I'm not even going to make my substitution. I've got this pattern recognized here. So what I'm going to do is, this is my u, this is my du, it's all there. I'm going to go up to 1, add 1 to the exponent, divide by that, so it's going to go up to 4 over 4 is going to give me 5/8 the quantity 2x plus 3 to the 4th power plus a constant. I'm going straight without actually making that substitution. If I need to make the substitution, if it's messing me up, make the substitution. There's my answer. Very similar, like I've got this expression right here. Now you look at it and you say, you know, I would probably just FOIL, write this as a long polynomial, and then integrate that. And I wouldn't have to mess with any of this stuff here. And you'd be fine doing that. It will work. However, if you think of this to the 1st power, and you think of this as your u, my u would be x to the 3rd plus x. Do you see that my du is 3x squared plus 1 dx? It's all there. 3x squared plus 1 quantity, excuse me, dx. So this is u to the n, and all this is my du. So this is going to give me up to 2 over 2, 1/2 times the quantity 3x, or x cubed plus x, to the 2nd power plus my constant. Look how nice that was. Now this guy's a little messier. I'm going to first rewrite him, because I'm not sure how to integrate an expression with this in the denominator. I'm going to write this as negative 4x times the quantity 1 minus 2x squared to the negative 3 dx. Now it maybe looks a little bit more like the general power rule, where this is my u. If my u is 1 minus 2x to the 3rd, my du would be negative 6x squared dx. Oh, hang on a second. Oh, that was a 2 there. Whew. That helps. Let's try that again. I take the derivative of this, I get negative 4x dx. Oh, look at that. Even better. That's all there. This is perfectly set up. This is my u to the n, my du. So up to negative 2 over negative 2 is going to give me negative 1/2 times the quantity 1 minus 2x squared to the negative 2 plus a constant. Now, I'm not going to leave my answer that way because I don't like the negative exponent, so I'm going to write this as negative 1 all over 2 times the quantity 1 minus 2x squared to the positive 2 power plus a constant. Don't forget your equal signs. This one is so nicely set up, it's a crime. My u is the sine of x. my du is the cosine of x dx. You couldn't ask for a better setup here. So up to 4 over 4, I get 1/4 sine to the 4th of x, sine of x to the 4th, plus my constant. Nice. Now, I got an asterisk next to this one, and my asterisk next to this one is because it looks like a general power rule where this is my u. So my du would be 2x dx. Now, I got the dx, and I can finagle the 2, but I don't have an x. So I cannot use the general power rule of integration for this problem. I am going to have to actually cube this, expand this out as a long polynomial, and then I can integrate. This would be the integral of, this would be x to the 6th plus 3x to the 4th plus 3x to the 2nd plus 1, if I didn't mess up when I cube that. And then this is going to be 1/7 x to the 7th, let's see, plus up to 5 over 5, 3/5 x to the 5th, up to 3 over 3, plus x to the 3rd, plus x, plus a constant. And there's my answer. So you have to be careful here. You can finagle a constant. You just can't do that with the variable there. Be very, very careful. Again, I'm sorry. I have a tendency to write on a tilt here, and I don't know why I don't position my body differently here, but there we go. That's our answer. I'll try to keep the paper straight for you guys. All right, now, time for stating another theorem here, but this time, notice it's for definite integrals. Now, we did definite integrals in the last section when we discussed the fundamental theorem of calculus, so I'm going to show you how you can use a substitution for a definite integral. We've been doing indefinite ones. If a function u equals g of x has a continuous derivative on a, b, and if f is continuous on the range of g, then the integral from a to b of f g of x g prime of x dx is equal to, now notice here, I'm making the substitution here that u is my g of x, and then I plug in here, if I change this into u, this has to be in terms of u. Because remember, u is the g of x. So I'll show you how that works. You're not only going to change this part and put it in terms of your variable u, but you have to change the limits of integration. Because see, these limits of integration are with respect to x. So if you're going to have it with respect to u, you've got to change these in a corresponding manner. So what I have here, my u is x squared plus 1, which means that my du is 2x dx. So right off the bat, I'm going to have to finagle a constant of 2 because I have the x, I have the dx, I need the 2. So I'm going to, here, I'll do this in red so you can see it a little bit better. I'm going to put the 2 here, I'm going to put the half here. So this is going to give me 1/2 the integral from 0 to 1 of 2x times the quantity x squared plus 1 to the 3rd power dx. Now my du is set up. So this is a 1/2. This is an integral. I'm going to get back to the 0 and 1. This part here, this is my u to the 3rd power du. Now what's going on here? Well, what happens with it when x is 0? Go back to the original substitution. When x is 0, if I put a 0 in there, that means u is 1. I always like saying that, when u is 1. U is 1. You know, you have to say you are for all the, you know, but u is 1. And then when x is 1, I substitute in, I find that u is 2. So instead of going from 0 to 1, in terms of u, I'm going from 1 to 2. Now it's just a coincidence that was just 1 more than that. That's not going to happen most times. But now I can integrate this. This is going to go up to 4 over 4, and I have a half there. So this is 1/8 u to the 4th running from 1 to 2. So this is 1/8. If I plug a 2 in there, 2 to the 4th is 16 times 16 minus 1/8. If I plug a 1 in there, I get a 1. So this is 1/8 of 16. That's 2 minus 1/8. So that's going to be 16/8 minus 1/8 is 15/8. There's my answer. Now there's a different thing that you can do with these problems when you're making this kind of with a definite integral. When I get to this point right here, if I decided to put it back in terms of x and put the x squared plus 1 in here raised to the 4th power, then I could go back to the original limits of integration of 0 and 1. I don't know if I have enough space to show you that. If I go back, I have 1/8. I make the substitution back in before I actually evaluate and write this as x squared plus 1 to the 4th power. But this time, instead of having 1 and 2, because that was in terms of u, if I go back to the original ones, 0 and 1, look what's going to happen. If I plug a 1 in here, I have 1 squared plus 1, which is 2 to the 4th power is 16. I get this. Minus, then I plug 0 in here, that's just going to be a 1 to the 4th power, it's just 1. So I get right back to there. If you want to make the substitution back in, then you have to put it back in terms of x, the limits of integration. Now this guy here, oh, he's a mess. All right, as you can see, this is the main part of my problem. I'm going to write this as the integral from 1 to 5 of the quantity 2x minus 1 to the negative 1/2 x dx. My u would be this part right here. I'm going to put them up here because I'm running out of space. My u would be 2x minus 1, so my du would be 2 dx. Now I can do the 2, I can finagle it, but I have that x there, so I have to rewrite this guy and put this guy in terms, x in terms of u. So I'm going to have to add 1, so I get 2x equals u plus 1. I get x equals 1/2 u plus 1/2. What? I got some serious substitution to make here. So this is going to be the integral. Okay, this is my u, so I got u to the negative 1/2. All right, then I have, where's my my x is this part right here. So that's going to be 1/2 u plus 1/2. And then what's my du? My du is 2 dx. Well, I've only got an x there, so got to finagle that constant, put a 2 here and a 1/2 here. And so now 2x dx, that's my du. So and then this is from 1 to 5. Almost forgot about my definite integral here. Well, this is all in terms of u, so I'm going to replace my 1 and 5 and put those in terms of u. So go back to the original substitution. If x is 1, this would be u is 1. And if x is 5, this would be a 9. Now that 1/2 right there, I'm going to factor that out. I'm going to write that. Now I already have a half there. I'm going to write this as 1/4 the integral from 1 to 9. And I'm going to distribute. Remember, the half's been factored out. So this is going to be u to the 1/2 plus u to the negative 1/2 du. Well, now I'm ready to integrate. I have 1/4. I'm going to just multiply through by the 1/4 at the end. So this is up to 3/2 over 3/2. It'd be 2/3 u to the 3/2. Up to 1/2 over 1/2 would be plus 2u to the 1/2, running from 1 to 9. So 1/4. Yikes. All right, 9 in there. That would be 27. That'd be 18 plus 6. That'd be 24 minus, plug 1 in. I get 2/3 plus 2. That'd be 2 and 2/3. That would be 8/3. So I have 1/4. This would be 72/3 minus 8/3 would be 64/3. And then 1/4 of 64, this 4 goes in there, 16, so I get 16/3. I told you that one was going to be a messy one. All right, we're going to finish this up with one very interesting theorem about integrating even and odd functions. All right, it says here, let f be integral on the open interval from opposite of a to a. Notice that these are opposites. That's key. If f is an even function, that means it's symmetric to the y-axis. Then the integral from the opposite of a to a of f of x dx is 2 times the integral from 0 to a. Now think about this. If I have an even function that's symmetric to the y-axis here, and I'm going from the opposite of a to a, this area should equal this area because of the symmetry. So instead of going from the opposite of a to a, if I just go from 0 to a, if I take half of it and double it, I get the same area. That's convenient because it's a lot easier to plug 0 in and evaluate expressions. If f is odd, which means it's symmetric to the origin, then the integral from the opposite of a to a of f of x dx is 0. Think about that. If I have this and I have this, then this area below cancels this area above, and I get an area of 0. So now, from the opposite of, from negative pi over 4 to pi over 4, the sine of x dx, the sine of x, that's an odd function. I don't have to go through all the steps. I could. I can integrate sine of x. It's negative cosine x. And then evaluate it here from negative pi over 2 to pi over, negative pi over 4 to pi over 4. I don't need to. I'm going to get 0. You can check me. And then for this one, that's an even function. I'm going from negative pi over 4 to pi over 4. This is the same as 2 times the integral from 0 to pi over 4 cosine of x dx. Well, when you integrate cosine, you get the sine of x running from 0 to pi over 4. If I plug pi over 4 in, the sine of pi over 4 is the square root of 2 over 2. If I plug 0 in, I just get 0. See how convenient that is? Plug 0 in. So that's 2 times the square root of 2 over 2, which is just the square root of 2. Makes my work a little bit easier, especially on this example. So practice these substitution problems for integrating composite functions, and it will make life in Chapter 5 so much nicer. Practice, practice, practice.